Alright, silly people, here's the situation. This is going to be a video about using the relaxation method, but with two variables instead of one. So we have this system of equations which, it describes glycolysis, but that's not really important. Um, you have this one that is a function of x and y, and this one that's a function of x and y. And the first part of the problem is to show that you can totally just solve for these equations analytically. And so that's what I did here. Uh, it's kind of just a usual systems of equations kind of proof thing. Um, this is the second equation that I actually started with. You can solve this for y fairly easily, and then plug that into the first equation, um, and then chug that along. Factor out a plus x squared, and then divide the equation by a plus x squared, so you get x equals b. Then you can plug that into the solution that you got up here to get b over a plus b squared. So that is certainly true analytically. The next part is to show that the equations can be rearranged to look like this. So you just go back to the initial equations for both of them, the first and the second equation, and just solve the first one for x and solve the second one for y. So yeah, solve this guy for x, solve this guy for y, and you get these guys. And we're going to write a program that is going to try and find the solution to the equation numerically, given the equations in these forms here. So we don't even need to import numpy or anything, but I am going to define a couple of functions. F of y and x, or x and y, this is going to be what we use to solve for x, and it's going to return that first equation there, which is y times a plus x squared, right? And then the other function, which is just a function of x, which is what we're going to use to solve for y, is given by b, or return b divided by a plus x squared. And now we can set up the over-relaxation method, or not over-relaxation, but regular relaxation. I'm going to get our desired accuracy up. It's 1e minus 6. Define a and b out here. So a was 1 and b was 2 in this particular situation. Get a initial value for the error. I'm just going to set it to be arbitrarily large, e to the 23, and also get initial guesses for what x and y are. I found that for this problem, if you just set it to 0.1, both of them to 0.1, then it can find the solutions, at least in the next part of the problem, they can find the solutions. But then you can do your while loop, so while error is greater than accuracy, you can set x1 equal to f of x1 and y1. Simultaneously, you want to make x2 equal to your old value for x1. Simultaneously, you want to make y1 equal to g of x1. And also, simultaneously, you want to make y2 equal to your old value of y1. Do it all in one line like that, or you're going to have some weird behavior. Now you want to calculate your error. I'm not going to use the actual relaxation method error formula that's in the book because it actually involves a derivative of something. And not both of these have, nice derivatives. And so I'm just going to use this standard error formula, which I'm going to take an absolute value of the maximum of the list, which includes x1 minus x2 over x1 and y1 minus y2 over y1. Yeah, just usual percent error formulas. I think I did that right. It's just that the brackets are a funky little color. And then at the end, we can have it print out what x1 and y1 are. And we're going to see that, oh, closing parentheses doesn't match. Get rid of a parentheses, or maybe add parentheses. That's not working. This parentheses works. Why does it not like this list here? Oh, because this parentheses is there. Okay, that looks good. And then get rid of those. There we go. You're going to see that this does not converge. It, in fact, is just going to run forever, bouncing between values because, you know, the relaxation method just kind of doesn't work for this particular set of equations here. So I'm just going to stop that. I'm going to stop it. No, don't run it again. Quit it. Okay, I stopped it. The next part of the problem is to resolve the equations in a way that the computer can actually solve for it. So yeah, that's part C. And it turns out a much better way of doing it is you set it up like this, where you're going to take essentially the equations that you left with last time. So these guys that you tried to plug in. But then solve this guy for y and solve this guy for x, and you get things which look like this instead. And so what we're going to do is we're going to copy down this old code up here, which did not work. And all we're going to do is going to change the function calls. So f of x will now only be a function of y, actually. It will return a square root. I'm going to import numpy so I can get that square root function. P. So yeah, it's going to return the square root of b over y minus a, and also g of x is now x over a plus x squared. And we're going to see how that looks. And I should get rid of x in the function call down there. But yeah, it actually converges and it gets the values that we expect it to. X1 equals b and y1 equals, 2 squared. It's 2 over 1 plus 2 squared, so 2/5. Yeah, and it gets that value pretty accurately.